Yeah, okay. Yeah, actually, I sent a mail on August of 12th, no? Same link only. Yeah. Okay, okay. Okay, okay, fine. Okay, okay. It will join actually. Yeah. Okay. Yeah.
Can forward this link to him so that.
Yeah, he got the link, but he is connecting from that WebEx link, but he's saying that that circle is coming like that. It's sure.
Okay, okay. The link is same only. The previous link and the current link is same only.
Yes, yes, the same link. He has clicked on that link only. I don't know what problem actually. Whether he is unable to connect or something.
Looks like.
This online actually is a big problem in India actually. Wherever you go, you don't get a correct connection anywhere.
Yeah, correct, correct. Actually, they are not used to it.
No, India, we don't have that type of network system actually. Robust system is not there.
Yeah, correct, correct.
This type of things never happen in abroad actually. Only here it happens.
No, actually, I attend many meetings, online meetings. They're very prompt in time. They'll join.
Very constant time and network actually doesn't fluctuate and nobody has any problem in connecting.
Yeah, correct. Actually, that NKN when it was started, I mean, during 2014 or 10, 12 like that. That time, they are not extended the proper fiber optical cables. They used existing one. Wherever they need, they simply extended.
Okay, okay.
They have to lay down the new cable with the new capacity, all the things, whereas they didn't do. Now only they are feeling that it is not enough. Now they are going for again,
Okay,
lay down the
okay.
cables. The backbone is as it is only. There is no change in the backbone connectivity.
Okay.
For Goa, we are having 10 Mbps, 10 Gbps connectivity from Bangalore, another one from Kolhapur. So only two, 10 plus 10, 20 Gbps connectivity only the entire Goa.
Okay.
So just imagine it now. It is not like earlier. How many? I mean, how many institutions have been grown? How many meetings are taking place? What are things are hosting on the web and many several meetings. So all these stakeholders, they have to provide within the 10, 20 Gbps connection only.
Okay.
Whether it is land based or anything else, they have to do like that one. Looks like he has some problem.
Yeah, it's appearing like that. I called him and he said it is connecting, and the link is showing some circle or something is coming there. And so let me call him again and see what he says.
Yeah.
Mm. Yes, so you are not able to connect. Ah. Okay, okay. Okay, fine, fine. Okay, okay. Okay, fine, fine. Fine, fine, no problem. Yeah, please. Yeah, I will send it again. Yeah. Yeah, same link only. I'll send it to you again. Yeah. Yeah.
Hello? Yeah, he has come, Raju. Your video has to on.
Okay. Yeah. Hello?
Yeah, your audio, yeah, fine, fine. You can start your presentation. No.
So voice is clear, right?
Yeah, it's very clear, very clear.
Right. I just want to check my slides once.
Yeah, please, please.
Okay. So.
So you can the slides. You can just open it actually. If you want.
Yes, sir. Yeah, and this is what I'm doing now. Screen.
So it is linked to the YouTube, no, Swami?
Yeah, it is already.
It's already
I set the timing automatically. It is automatically started.
automatically started. Okay, fine. Yes, Professor Raju, it is fine. So it is fine. Yeah, you can make it in the full
Yeah,
screen, full screen mode.
full. Yeah.
Yeah.
Is that running well? Running well, sir? All the slides.
Yeah, I can see the first slide actually. Yeah. But it can be made in the full screen. Yeah, full screen mode. It is not yet in the full screen. You can make it full screen mode.
It's already. Cannot.
Yeah, fine. You can go ahead.
We can go. Okay, fine. So good evening. Actually, good evening to all the esteemed members of OSI, ladies and gentlemen. So the Ocean Society of India, it conducts the invited talks as a part of this webinar series once in every month. And this talk is arranged from eminent scientists, engineers, and academic professionals working in the broad areas of atmospheric and oceanic sciences, ocean engineering and technology, and allied disciplines. So this webinar is mainly targeted for the students, researchers, scientists, engineers, and working professionals in the field of atmospheric, oceanic sciences, ocean engineering and technology, with a motive to impart and improve the knowledge benefiting the OSI community. So I request all the members to actively participate and get involved in all the lectures under the OSI webinar series that is held every month. On behalf of OSI, it is my proud privilege today to welcome Dr. Attada Raju, Assistant Professor, Indian Institute of Science Education and Research, IISER, Mohali, and he will be delivering a talk on the topic Indian Summer Monsoon in a Regional Modeling and Data Assimilation Framework, a topic which is of relevance for the meteorologists, oceanographers, and allied disciplines. Professor Attada Raju actually obtained his bachelor's degree in computer science from Andhra University in 2005 and master's degree in meteorology from Andhra University in 2008. He obtained the PhD in atmospheric sciences from the Indian Institute of Tropical Meteorology, IITM Pune, in 2015. So Professor Raju is a very serious researcher and a dedicated scientist, having exemplary track record in research and publications in high-impact peer-reviewed journals. So his research interests are on varied topics such as regional climate modeling, data assimilation, weather and climate prediction, Indian summer monsoon and large-scale dynamics, climate variability and climate change, studying and predicting the weather and climate extremes. So after completing his PhD from IITM Pune, Professor Raju worked as a research associate at IITM Pune during September 2014 to June 2015. He also worked as a visiting researcher at the King Abdullah University of Science and Technology, Kingdom of Saudi Arabia, from 1st of January to 30th of January 2015, and postdoctoral researcher at King Abdullah University of Science and Technology, Kingdom of Saudi Arabia, from June 2015 to April 2019, and assistant professor at Indian Institute of Science Education and Research, IISER, Mohali, from April 2019 till present. So Professor Attada Raju received the Best Research Award in the International Conference of Climate Modeling and Climate Change Research, Innovation and Services, and CSIR Net Award from the Government of India. Dr. Raju is a life member of the Indian Meteorological Society, the Ocean Society of India, the Asia Oceanic Geoscience Society, annual member, the European Geoscience Union, which is an annual member, and he has published about 40 peer-reviewed papers in reputed national and international journals, and presently guiding 3 PhD students and 2 project JRFs. He has guided 4 BS MS students and presently guiding 2 students. So Professor Raju is also a PI of for 3 DST projects, ISRO and MOES projects. He is a PhD convener in the Department of Earth and Environmental Sciences, and also the warden in the Dean Students Office and Senate member of IISER Mohali. So with this brief introduction, it is my proud privilege to kindly invite our speaker for today, Dr. Attada Raju, to deliver the talk. So it is also requested that this questions and answers session can be attended after completing the talk, and the questions can be messaged in for the speaker in the chat box. So thank you. So with this brief introduction, I request Professor Raju to deliver the talk. Thank you.
Thank you, sir. Good evening, all. Thank you for a wonderful introduction. We are running late, so the topic of the today's talk is Indian summer monsoon system in a regional modeling and a data assimilation framework. So I mostly focus on the how the monsoons, Indian summer monsoon, can be represented in the regional modeling context, and what are the ways to improve the monsoon modeling in a regional model. So this is a brief outline of this talk. The first I will be covering the background of the Indian summer monsoon system, which will be useful for graduate and undergraduate students. And then secondly, I will focus on the how the model represents the monsoon characteristics and what are the key challenges, and finally some ways to enhance or improve the model fidelity in terms of monsoon simulation, prediction, and predictability. Okay, as we all know, the monsoon is the spectacular occurrence in the Earth's climate system, and in fact, it acts as a monsoon engine, which grabs the moist laden winds in all the way from thousands of miles from the Indian Ocean towards the Indian land region, and gives the large amount of rainfall. So the what is the monsoon? The monsoon word is actually coined, is actually derived or stemmed from the word Arabic word mausam, which means the season. So which strictly speaking, the means that the seasonal change in the wind direction. As I pointed out, the Indian summer monsoon system is one of the strongest monsoon systems in the world. Okay, if you look into the image at the center, you see this is average all Indian monsoon rainfall from January to December months over the period of 40-50 years. So what you can see, the most of rainfall can be noticed between June and September months. So this system occurs every year. It brings a lot of rain during the summer months. So that is why it is a summer monsoon season. Though it is homogeneous in terms of temporal scale, every year, but it is highly heterogeneous spatially, because one year it may give a lot of rainfall, or one part of the world or one part of the subcontinent can receive a lot of rainfall, and it can end up with the floods, and other parts of the subcontinent in the same year can receive no rainfall or very less rainfall, and that can cause for catastrophic drought conditions. Okay, so therefore the monsoon rainfall is very important for many aspects. Okay, especially for the people who is living in this region. Most of us actually rely on the rainfed agriculture, and also ultimately controls the economy of the country, along with the other conditions such as water resources and power generation. So the definition of the monsoon is a large-scale land and sea breeze system that is mainly caused by the thermal gradient between the Indian subcontinent and the Indian Ocean. As I said, so it occurs every year between June to September month, and it is also believed to be a seasonal manifestation of the northward migration of intertropical convergence zone. So just to illustrate this seasonal manifestation of intertropical convergence zone, if you look into this winter months, this is the rainfall patterns. Rainfall is mostly confined, in the equator or south of the equator. But in the summer, as the sun moves, the northward migration of this rainfall band or maximum rainfall band can be seen of the entire subcontinent. So this is what the seasonal manifestation of intertropical convergence shown. Okay, so how can you define a monsoon regime or a monsoon region? According to Ramaje, he proposed a certain criteria to define the monsoon region. So those conditions are strictly pertaining to the pressure patterns and circulation patterns. For example, the prevailing winds should shift at least 120 degrees between the one season to other season. The average frequency of prevailing wind direction should be more than 40% between one to other season. The mean wind speed, prevailing wind speed, should exceed 3 meters per second at least. And along with this, the pressure patterns should satisfy the steadiness criteria. So according to these conditions, so Indian summer monsoon region is one of the most eligible or well-fitted monsoon region, along with other monsoon regions such as West African monsoon region, some North Australian parts of region. In addition to that, recently North American monsoon has also become is emerging. So this part is also coming into these conditions. Okay, what are the important physical drivers of the monsoon system? The first and foremost driver is differential heating between the land and ocean. So, as we know, we have the land, we have the large ocean body south of the Indian subcontinent. This water can have the more specific heat, than the land, which is about 3.3 factors higher. So which means that it has a large capacity to store the heat and compared to land. And this heating at the surface level sets up the thermal contrast between the land mass and ocean and the respective pressure gradients between the land and ocean. This meridional pressure gradient drives the winds from the ocean to land mass. In addition to that, due to the solar seasonal cycle of the solar heating, uh, landward migration of ITCZ, as I pointed out in last slide, and also third important factor is Earth's rotation. So because of the Earth's rotation, the Coriolis force arises, and this Coriolis force can drive the monsoon circulation in corporate path. Otherwise, would have been straight lines from here to there. The last process is very important process because it actually maintains the monsoon system for next 4 months, like for example June 1st to end of the September. So the basic principle or the basic physics behind this moist process is, as the moist air rises over the heated land surface, over the land surface, so it causes the thermal instability. So this moisture eventually condenses and ultimately releases lot of heat energy. This energy maintain the land and sea pressure gradients, and finally to add the monsoon over the season, that is from July, August, September, appreciation of the differential heat. So fundamentally, differential heating at the surface is important to establish or to moist process is intriguing feature of the tropospheric gradient that causes intensity and that maintains and intensify the monsoon system further. Okay. So, for example, look into this image. The rainfall is the function of latitude with the time. You can see the northward migration of the rainfall pattern, especially during the monsoon months. And the line, black line, represents the kinetic energy. You can see the rapid and strong kinetic energy during the summer monsoon months. So there is a clear association between the kinetic energy, the Arabian Sea, and the monsoon rainfall over the land region. You see tropospheric gradient, temperature which is averaged between the average a layer between 700 hectopascal to say 300 hectopascal. So the temperature is almost 8 to 9 degrees centigrade is warmer over the land region. These are the land latitudes, and these are the ocean latitudes. So comparative to the ocean, land is actually 8 to 9 degrees centigrade warmer. So you can see the temperature gradient in the tropospheric level, where it can drive the monsoon winds, as I mentioned in the last slide. So the moist convective process is very important again to maintain the monsoon. Okay, so these are some basics, and the monsoon rainfall is actually the final output, but there are many ingredients to get this monsoon rainfall. Such gradients are actually proposed by the Krishnamurthy and Palme in 1976. That can be seen in this box. namely heat low and monsoon trough, cross equatorial flow and the low level jet stream, masculine high pressure system, Tibetan anticyclone, tropical easterly jet stream. So altogether can produce monsoon clouds and then rainfall. Okay, if you put all these elements are ingredients in the box, this is how you can visualize. For example, masculine high starts somewhere in the southern latitudes, and there is a low level jet stream, monsoon trough down, and there is a Tibetan anticyclone, and also associated tropical easterly jet stream, and then finally rainfall along with the monsoon clouds. So I just would like to give a brief description about all these elements to just to know the basics about it. So heat low is the one of the first indicators of the monsoon or monsoons, where because of the intense solar heating, it receives the maximum amount of solar insolation in this part of the world, where it can form as a low pressure system with the ice with closed isobar about 994 hectopascal. Okay, so this is actually important, and in fact it is an extension of the monsoon trough. But the depth of the heat low is very shallow, and in fact it is only up to 1.5 kilometers from the surface, where the upper air can subside over this heat low, and then that inhibits the convection. And in fact, there is no moisture availability at this point of time, that is somewhere in the May. So therefore, it is mostly end up with the dry convection, and therefore there is no rainfall. But the important element is that this element is useful to know the establishment of monsoon. It is a kind of indication, the first indication of the monsoon system. The secondly, the monsoon trough. In fact, the monsoon trough is an extension of the heat low over the northwest India. It slowly, extends towards the head bay of Bengal across the Indo-Gangetic plain. So the monsoon trough is east-west oriented low pressure system across the foothills of Himalayas. This is one of the important elements as well, because it is always often associated with the heavy rainfall amounts across this belt. But it is not quasi-stationary. It always moves from its normal position towards the south and north. And whenever it moves south from its north from its normal position, say for example along the foothills of Himalayas, you can receive, there is a remarkable change in the rainfall patterns. You get more rainfall, in the across the foothills of Himalayas. At the same time, a paradoxical situation can be seen at the other parts of the country where there is no rainfall. Okay, but when the monsoon trough moves towards the south from its normal position, then say, the entire country or most of the Indian subcontinent receives good amount of rainfall except the foothills of Himalayas. So basically, this displacement from its normal position, can determine the active or the break phases of the monsoon system, and this is very important because the monsoon performance is actually depends upon the dynamics of this monsoon trough. Okay, but but unlike the heat low, the northwest heat low, this is it's much deeper, where it can the humidity or the moisture can go up to the troposphere in the southern flank of the monsoon trough region than the eastern flank of the region than the western flank of the region. This western flank is basically represents the heat low, other side, and this is the monsoon trough. So the other important element is masculine high pressure system, which is basically can be seen in the southern parts between the 25 degrees south to 35 degrees south and 40 degrees to 90 degrees east. This is in fact the source of monsoonal winds, and it has a highly connection with the monsoon trough region. So monsoon trough region is a kind of heat source, whereas the masculine high pressure system is a heat sink. Okay? Therefore, the position and intensity of this system, the masculine high pressure system, is considered to be closely linked to the monsoon activity. In case of there is a delay in the formation or the weak formation, it always dictates the performance of the monsoon rainfall in India. Coming to the cross equatorial flow, the winds actually starts from the masculine high pressure system and it crosses because of the Coriolis force. All the winds will be deflected, and these winds can carry a lot of moisture towards the Indian region. Right? So, and it attains the maximum wind speed at the half of the Somalia coast. So, the maximum wind speeds can be seen at 1.5 kilometers height from the surface, which can be 18 to 20 meters per second. This is the core of the monsoon, core of the low-level jet. This monsoon element is very important, and as you know, it carries a lot of moisture from the warm waters from the Arabian Sea, and then gives the rainfall over this region. Coming to the Tibetan anticyclone or Tibetan high pressure system, so this is one of the most remarkable circulation system in the upper atmosphere during the summer. So this is a very large anticyclone system, often can be seen at 200 hectopascal for the Tibetan plateau. This is basically down below the anticyclonic system. There is a monsoon trough where the lot of winds gets converged and then diverge in the upper levels and then become and then the winds can be clockwise rotation, and then it is a anticyclone system. So this anticyclonic system is basically linked with the sensible heating of the Tibetan plateau. Basically, Tibetan plateau plays very important role in forming the Tibetan anticyclonic system for this region. And this is also one of the important key factors in the development of monsoon circulations in the region. The movement of high pressure core, warm core, is also determines the performance of the monsoon activity in Indian region. So, if you look into the mean temperature between these layers, you see there's much more warming can be seen over the Indian continent than the oceans. So, therefore, I mean, as I said, there is a monsoon trough, and all the winds get converged at the surface and move upward and diverges, and it spreads out the both south as well as north, and this helps in moving the circulation or moving the winds towards the south side. For example, look into this cross section. So all the winds go up and then move towards the southern latitudes and then sink somewhere in the masculine high pressure region, and then so that is where this is the heat sink and this is the heat source, and then at the surface level the again winds will go as southwesterly and then connects. So this cell is popularly known as Hadley circulation or monsoon Hadley circulation. The other important element is, especially upper atmospheric element, is tropical easterly jet stream. So tropical easterly jet stream is actually associated with the Tibetan plateau again, and it mostly can be seen in the southern Indian region, all the way from East Asia to Africa. The strongest development of this jet is about 15 kilometers above the Earth's surface, with the maximum wind speeds about 40 meters per second over the Indian Ocean. You can see these red colors. This is still again connections with the sensible heating and also condensational heating of the Indian continent and Tibetan plateau region. So the last thing is the rainfall. This is the final output with the help of other inputs. Okay? So the rainfall pattern. This is the long-term mean summer precipitation during the June, July, August months. Then you can see the lot of strongest mountains over, and because of geographic activity, we get more rain. Again, we have the mountains here, and then you can see the wettest part in the world, and also central India. This is rainfall along the eastern equatorial Indian Ocean. So if you average all India rainfall, we can. So this is the annual cycle. Rainfall. If you all this, and this is what you can see. Okay, so mass pressure system, jet, and the black also jet. Wow. Helps.
Raju, look like your internet was stopped.
I think he got that got disconnected actually. Again, he joined now. Yeah.
Yeah, please let him
Sir, I
continue.
was not aware of it. Again, anyway, I'm just sharing.
Yeah.
Is the same slide I'm talking about, or something else? Sir?
Now, yeah, hit the same slide actually. You can make it in the full mode actually, full screen mode.
Yeah, I don't know. It is going so fast.
Uh,
Yeah, can I start now, sir?
Yeah, you can start, please.
Okay, so let me put this monsoon theory as a prototype monsoon theory, and because of the solar energy, we have meridional pressure gradient, and that leads to the driving the monsoon winds, and then they converge and then move upward, and then condensation takes place. The clouds form, and then we get rainfall, and then that releases a lot of latent heat that actually warms the troposphere, and then sets up the pressure gradient between the Indian subcontinent and the oceans. In addition to that, Tibetan Plateau also acts as a heat pump. So together, again, that sets up meridional heat. Further, drives the monsoon circulation and then maintains the monsoon for next 3 months. This is a simple, monsoon theory. So based on these elements, but in addition to that, we have other synoptic weather systems that is metropospheric cyclones, offshore vortices, and monsoon lows and depressions, along with the monsoon trough, and also orography is also playing. For example, this onset vortex can give the lot of rainfall in the Kerala and or the Western Ghat region, whereas the mid-tropospheric circulations, where this type of circulations can be seen only in the mid-troposphere but not at the surface. This can also determine some amount of rainfall in the Gujarat and adjoining regions. The monsoon depressions are the westward movement low pressure systems that can also give the good amount of rainfall. So the monsoon is actually it's not so easy. It is a complex phenomenon where there are many scales of interactions takes place and that gives the rainfall during the monsoon season, starting from June to September 30. So, getting this real picture, into the virtual or into the modern system is much more difficult, and that is where we are always, failing to get the real prediction of the monsoon. Okay? So, but see, like how these models can be seen. So, based on the governing equations of equations of the fluid, which actually starts from the wind forecasting equation, where you have the horizontal advection of the wind, vertical advection of the wind, and then some forces, fundamental forces, including Coriolis force and then pressure gradient force and frictional force, where it is very important at the surface. Similarly, meridional wind equation, same, and then continuity equation where it can determines the vertical velocity, and temperature forecasting equation where you have the horizontal advection of the temperature, meridional and vertical advection, and also some other processes such as diabatic heating and so on and so forth. And then this is the moisture forecasting equation. So all these equations are considered and then solved at every grid. At every grid, for example, the grid can be seen as something like this, where you have the 4 points, and it is not only at the surface, but you have the multi levels across the vertical axis. So you have to solve all these equations at every grid point, not only at the surface, but also up to the troposphere in order to get the monsoon characteristics. Okay, so in addition to these equations, there is a lot of physics involved, where the water vapor dynamics and thermodynamics and radiative transfers, and also a lot of input from the ocean, where it can give the continuous feedback to maintain the monsoon. Okay, so so we need to parameterize all this process in a simple way. So these are some physical parameterization. The processes needs to be parameterized. For example, incoming radiation and their interactions with the clouds and aerosols and precipitation. There is a heating, and you have runoff and vegetation, land surface processes. All these process needs to be parameterized in the model. I think now you understand the complexity of the modeling, and along with the complexity of the system, monsoon system. So here, what I did, we use weather research and forecasting model as a numerical weather prediction model to simulate the monsoon system for 15 years. So this is the model domain integration, where it covers the entire region as suggested by Ramaje. I have showed in one of the earlier slides. So these are the different physical processes. For example, convection can be resolved by this particular scheme called Betz, Miller and Janjic, which is the best and PBL scheme. And there are microphysics cloud process can be resolved by using this, and the radiation scheme, both short wave and long wave radiations, can be resolved by these radiation schemes. And also land surface, the soil moisture and precipitation feedbacks and soil moisture feedbacks to the atmosphere can be resolved by using this parameterization scheme. Along with this, sea surface temperature is very important because it always gives the good feedback. So it is always continuously given as a prescribed format, along with these important initial and boundary conditions from this database, which is National Center for Environmental Prediction System. Okay, at the resolution of 111 kilometers into 111 kilometers. So this is all about the model and experimental design, but let us see the results, how they look like. I think we already discussed the monsoon elements very clearly. So this is the era I is the data where it can be used as the it can be used as a reference or validating the model results, and also can estimate the bias. Okay, first of all, let us look into the era 5. As we discussed, we have the pressure gradient because high pressure here, low pressure there, and that drives the monsoon winds and at the lower levels, and also in the upper level UV 200 means U wind, V wind at 200 hectopascal, where you can see the strong tropical easterly jet stream that as we discussed it before, and then there is a Tibetan anticyclone and then monsoon rainfall distribution. Okay, where you see the rainfall over the Western Ghats and rainfall over the Bay of Bengal and Myanmar regions and Central Indian region, and then Equatorial Indian region. So this data is showing well. So mostly observed characteristics. And coming to the model, you see
I
such.
think, Professor Raju, the slide actually is not moving. I think slide. It is still in the monsoon theory only. No, yeah, now it is okay. Now it is okay. Now it is okay. Yeah.
Okay, so I think I should not put it in the slide mode, full slide mode, because it's not moving. So,
okay.
sir, then I think I have to repeat the same thing. Let me go back.
Yeah.
This equation part, is that came before or?
No, it has not come. Yeah.
Okay, so just briefly, I will be repeating the same thing.
Yeah.
Anyway, these are the set of equations that can be used to build a model to simulate the atmospheric phenomena. But in our case, the monsoons. Okay. This is the model experimental design, and where it can be used, data can be taken from the FNL data to drive the monsoon, and other, in addition to other physical parameterization, convection, boundary layer convection, cloud processes, radiation, and land surface can be resolved by using these physical parameterization schemes in the model integration domain. Okay, so these are the some results. So ERA 5, I think you are missing the point. So ERA 5 is the data which can be used as the model validate. It can be used as the reference data for the model outputs. So these are the model data. But what we can see is that the model is general characteristics, monsoon characteristics such as pressure gradient between the ocean and land can be reproduced, and winds, low level winds such as Somalia jet and cross equatorial flow, and also tropical easterly jet stream and upper level Tibetan anticyclone system, and then monsoon rainfall can be seen. But however, when you look into the bias or the difference between the model and ERA, so you can see there is a asymmetric bias, especially in the sea level pressure distribution, which is the one of the ingredient of the monsoon winds and therefore the rainfall pattern. There is a bias here, and also that causes for the broader low level jet stream, and its course shifted mostly towards the southeastward from its normal position, and the tropical eastern jet stream is also slightly weaker than the observations, and more importantly, you can see the intertropical convergence type of double ITCC type of precipitation bias in the southern Indian Ocean, which is the most common in the many climate models. So most of the climate models, which is linked with other physical processes and also from the daily connection patterns. Okay, so this is the seasonal evolution of rainfall over the monsoon core region. This is the monsoon core region, which represents the 99% of rainfall over the Indian region. So where you can see the seasonal cycle of daily climatology from the model and the other two data sets. One is satellite data sets as well as the station-based observational data sets. What you can see in the model is that model is overestimated. In fact, model is producing more rainfall than the observations, and which can be seen in the northward migration of the maximum rainfall band. For example, TRMM and GPC's rainfall is relatively lower, than the model observations, model data, and the way the model, the northward limit of this maximum rainfall band is mostly limited below the 23 degrees north, whereas these two data sets shows the limit is up to 28 degrees north. There is a shortfall in terms of northward limit of the monsoon, northward limit of the maximum rainfall band. So this can actually significantly affect the rainfall patterns in India. Okay? So just to know the reasons for this, the highest rainfall bias, we have checked the moisture and thermodynamic structures for the monsoon core region. This is in this box. So what you can see is that though the mean average profiles are okay, but when it look into the seasonal daily climatology, there are a lot of issues in terms of temperature distribution as well as the moisture distribution. For example, moisture in the model, this is the model output, this is ERA 5 observations. Okay, in the model compared to observations, we have a lot of feeded with the water vapor, Okay, that actually causes for the stronger instability than the observed, and that leads to produce more and more rainfall, and that finally affects the variability nature of the circulation system. For example, zonal wind, if you plot the zonal wind of this region, you see the model produces a very weak variability structure, which means that there is a weak westerly winds at the down, and also comparatively the upper atmospheric winds are also a little bit different than the observations. And within the monsoon season, we also have the active and break phases. So active means you get more rainfall than the normal. Break phases means you don't receive rainfall or the less rainfall than the normal. Okay, so these are also very important. And model is actually getting right picture in terms of spatial distribution, but the intensity are the significant intensities are actually showing a lot of discrepancies. Okay, and when you look into the lead lag evolution of these temperature profiles or the moisture profiles during these ISOs, intraseasonal oscillations, that is active phase and break phase. Like for example, this is the lead lag evolution where 0 represents the maximum rainfall day. Okay, it is a composites of several active rainfall cases, and then back to 15 days and ahead of 15 days. So at the time of maximum intraseasonal rainfall day, so these are the two different data sets. Okay, sorry, these are the two different data sets. One is satellite data, other one is reanalysis data. What you can see is that both the data sets can at the 0th day or the maximum intraseasonal rainfall day, you have a strong baroclinic heating structure, right? Where you have the strong heating in the upper atmosphere and middle atmosphere, but cooling at the down. Okay, which is clear in the era reanalysis data as well. Importantly, there is a strong warming at the surface. This is something called preconditioning to this active phase of the maximum rainfall day. So if you look into the model result, model is showing the baroclinic structure where you can see the warming in the upper and middle atmosphere, much more cooling in the down. But overall, it is weaker than the satellite as well as the reanalysis data sets. But importantly, the model missing the preconditioning to this peak intraseasonal rainfall. So there is a issue in getting the preconditioning to the active intraseasonal rainfall. The similar disparities can be seen in the lake conditions. Okay, coming to the water profile, it is very similar to the previous slide, but but in the case of water vapor, in generally, so in order to get the maximum rainfall at 0th day, so the moisture needs to be accumulated, with the height. This is height with the height, and then when it reaches to its maximum, then it pours the rainfall, and then the entire troposphere is going to be dry. Okay, so this is how a systematic evolution of the systematic evolution of water vapor during the intraseasonal evolution. Okay, such systematic evolution of the moisture is actually absent in the model, where you see more water vapor is always present in the lower atmosphere. It's not showing any drying, especially in this after the rainfall. So this is a kind of significant bias in the evolution of the moist process, especially at the active break cycles. Okay, so what is the story, or what is the key message from these results? So there are discrepancies in the model, especially model exhibits weak land and sea thermal contrast that leads to the weak meridional sea level pressure gradients, and then that affects the circulation in terms of the lower atmosphere circulation as well as the upper atmosphere circulation, and that actually then misses the rainfall patterns as well as the northward limit of the maximum rainfall band, and the associated moist and convective processes are feedbacks are limited, improper, and then finally you are not getting the good monsoon simulation as in the observations. Okay, the first question is that how can we resolve these shortfalls in the model physics, and then of course by using the moisture and thermodynamic structures, because these are the important elements that affects the performance of the model as far as the WRF concerned. Okay, these three elements, these three discrepancies can be resolved to some extent by using the accurate temperature data. If you have the good temperature in the model, so all these things will be fixed out. And if you have the water vapor, Q means water vapor. If you have the Q water vapor, the moisture conductor process, and then associated feedbacks can be resolved, and then you may get better rainfall and better rainfall distribution. Okay, and then better thermodynamic feedbacks. That is the idea. Okay, so then how can we do that? So this one way is the data assimilation. Here in this case, 4-dimensional data assimilation is considered. So data assimilation means it is the bridge between the observations as well as the numerical models, where it can bring the solutions can be can be the best optimal, and then brings the best synergy. Okay, so the data, if you have the temperature or water vapor data, continuously you can assimilate in the model and then correct the model errors and then make it better, better inputs to the model, and then and then further improves and then you will get the better picture. That is the basic philosophy of data assimilation. So, but only the problem is that where to get the temperature and water vapor profiles. Earlier we used to rely on the and the radios and the observations where it is very limited, but unfortunately we have the unprecedented data set coming from the atmospheric infrared sounder, where it will give the lot of observations. In fact, 3 lakh profiles can be given across the world in a day. Okay, this is one of the best data sets available, and that we have assimilated in this in the model, especially WF model, to see whether we can improve those shortfalls, or whether we can improve the monsoon system in the WF. Okay, so the rationale is that, like, according to the linear adjustment theory, if you have the accurate temperature structures that can adjust, or that can improve the wind feeds and vice versa. That was actually theory was given way back in 1964 by Washington, Ramat, and so many people. And in addition to that, if you assimilate the moisture content, and then that is that can improve the convective process, and which is the important or fundamental driving force for the for the Indian summer monsoon system. For example, look into this schematic. So this schematic can tell you, if you adjust the temperature profile, so you can see that you can improve the wind, or if you touch the wind, or there is a improvement in the temperature profile and associated warming and circulation characteristics. So that means there is a dynamical linkage between the temperature and then wind feeds. So that is the idea, and we assimilated using the atmospheric infrared data, both the T and the Q profiles. T means temperature, Q means water vapor profile in the model. So now you see there are 3 panels. One is control. Control means no assimilation, or I can say old model, so a biased model. Now TQEXP, that means T and Q assimilated or assimilated model. Okay, this is old model, this is assimilated model, and era I as a reference. Okay, so now you can see that there is an improvement in TQXP, that means new model. When we assimilate Q and Q profile, sea level pressure distribution as well as the mid-tropospheric temperatures are better. That can be seen especially when you look at the differences. The control, the old model, there is a asymmetric sea level pressure differences here, right? So in the case of the new model, so those biases are almost minimized, and in fact very minimal errors can be seen. And also the tropospheric temperature gradient evolution is also better in the new model than the old. Okay, so the first indication is that sea level pressure distribution and the mid-tropospheric temperatures are better. So then one can expect realistic realistic circulation patterns, right? So this is what we have done here. Again, if you look into this arrow, that is a new model. Compared to era 5, these 2 panels are much more closer to each other than the control. Okay, that means low level jet stream and then cross equatorial flow is much better in the assimilator model, or in the model where we assimilate P profile and Q profile. And similarly, upper atmospheric circulation, for example, we know we have a Tibetan anticyclone as well as the tropical easterly jet stream during the summer, right? And if you look into this control, for example, just look into the letter H, it means that high pressure system. This is actually towards the west from its normal position if you compare the era 5, right? So this H is much more closer in the PQXP, the new model. So that means the core of the anticyclone is well represented in the assimilator model than the control or the old model. And also tropical easterly jet stream intensity as well as the position is much more closer in the new assimilator model can be controlled. In addition to that, vertical wind shear, which is one of the important diagnosed element where it can drives the instability of the atmosphere or unstable atmosphere. So compared to the control, TQEXP and ERA5 produces a better distribution, especially in terms of wind shear. Okay? And look into the meridional distribution of thermodynamic variable, because these meridional distribution, meridional means with respect to latitude, with the latitude over the Indian longitude regions, okay, between 70 to 90 degrees or 70 to 90 degrees longitudes. Okay, this is very important because we have a problem in the northward limit of the maximum rainfall band. So if you have the better, characteristics of all these variables, we can get better northward limit of the maximum rainfall zone, which is actually limited in 23 degrees north, the control. What you can see, especially look into the blue and red lines. Blue and red lines are the observations and the new model. Most of these lines are much more closer, right, than the black line. Black line is the old model, control model. So that means there is an improvement in the meridional distribution of all these thermodynamic variables. In addition to that, temporal execution of monsoon associated fields, like for example, zonal wind, relative vorticity, temperature, water depth, and finally rainfall. Rainfall, you see, as we noticed before, rainfall is much more higher in the wet bias in the control model, whereas in the new model, that is green line, red line, showed the significant reduction in the wet bias. Though there are some issues at the end of the monsoon season, but it is better, okay, with the better correlation of about 0.5. Okay, these are the different monsoon indices that can be represented the daily activity in terms of zonal wind, meridional wind, rainfall at three different heat source regions. So all of these images or all of these plots can show that assimilating T profile and Q profile can improve the daily monsoon regional indices with the the statistical pattern, spatial pattern correlation or temporal correlations. It's always better than the old model. That is another important message. And these are all related to circulation. And coming to the moist convective process or moisture distribution, in the control, this is the moisture static energy. The contours are the precipitable water. So in the control, we have the lot of moisture, precipitable water, as well as the moist static energy, which is actually the spatial extent is much more wider. But in the case of new model, the simulated model, the spatial distribution is much more closer to the ERA5. Secondly, if you plot the relative humidity and then moist static energy across the monsoon trough axis, so the control patterns are much different than the ERA5, and in fact, PQEXP patterns are much closer to the ERA-I data. So that means the moist convective processes or the moisture distribution is also important, and it is also improved in the new model. Okay. Okay, so all these things are actually further confirmed by these statistics, where it can shows the correlations are always better. Hello, sir, can I see my slide?
Yes, it is visible.
Okay.
Yeah.
Right. Sorry. Yeah. Okay. So right now the key message is that so far, assimilation or the correcting the temperature and water vapor profiles in the model, especially touching the model physics, can improve the moist and thermodynamic structures directly, and that can improve the representation of land and sea thermal contrast, okay, which is the triggering monsoon mechanism, and then improve the circulation and the associated baroclinic structures, and then finally modify the deep convective process that can closely linked to the heating structures and related heat releases and all, and then that can further set up and maintain the monsoon circulation well. And then finally we get the better moist convective process and then rainfall structures. So whatever the problem noticed in the control or the old model is resolved by just assimilating temperature and water vapor profiles. So in order to get the better monsoons in the model, this is one of the ways to fix it out. Now, can we check if the forecast has improved or not? So we have used bit advanced assimilation techniques and also more experiments and more data. I'm not going to discuss. If you want, we have a paper in GEOGR atmospheres. One can go through details, and if you want, you can send me the questions. So the initial check is that whether the assimilation of temperature and water vapor profiles at the initial state or the what we call initial conditions are improved or not. So in the case of, for example, a black line is the control, and the other two lines are the two different experiments, basically just to different purpose. But what is important here for us is that when compared to the black line, the other lines are always lower because it exhibits lower RMSEs. These are the RMSE profiles, error profiles. Okay, that means control has more errors than the assimilative model. Okay, both in terms of temperature as well as the water vapor mixing ratio. So it means that the quality of the initial conditions are improved when we, especially the temperature and the water vapor profiles, when we assimilate the model. Okay. Now, obviously, one can expect better rainfall prediction. Let us see how it can be seen. This is a one way of our presentation to see the improvement or degradation by assimilating the temperature and water vapor profiles in the model. Okay. For example, positive values means improved than the old model. The negative values means degradation. Okay, we have just checked with, this is the formula, we have just checked with the low level zonal wind and upper level zonal wind, and also relative humidity and rainfall. So most of the cases the rainfall, the prediction of the zonal wind at 850 hectopascal improved, and of course the upper level wind also improved, relative humidity also improved, and rainfall is also improved. Okay, but although there are some issues in the in the central Indian region, where it can be linked to the boundary conditions, because we have improved only initial conditions. Okay, so these are some mean states. Okay, so the mean state, for example, this is ERA, and this is the for this is the pressure. Sorry, troposphere temperature and humidity. This is the reference, and this is the assimilated model. Okay, prediction. So you can look into these two patterns. They are much more closer to each other, and not only this temperature and humidity, specific humidity patterns, but also rainfall, some extent rainfall characters as well. So these are some statistics, where it can be there are sea level pressure, upper level wind, lower level wind, tropospheric temperature, the specific humidity and rainfall. In most of the cases, the simulated model can give the better prediction of the monsoon rainfall. So, okay, so just quickly talk about the predictability, the predictability of different monsoon regimes, monsoon weather. For example, in the monsoon, we have active phase, that is active weather, active monsoon regime, and break monsoon regime. So active monsoon regime, we get more rainfall. Break means we don't get much rainfall. In fact, very less rainfall. Okay. So the predictability of these two aspects or two phases are very important, because the background, the active monsoon regime is actually controlled by more linear non-linear error growth, but the break is relatively better. So predictability can be expected better for the break phases than the active phases. Okay, so what is the predictability? Predictability is the degree of accuracy with which it is possible to predict the future state of the system. In our case, active weather system or the break monsoon weather system. Okay, so to do that, we have done twin perturbation experiments with the two different data sets. One is the control data, other one, like I can say, one is the old model, the other one is new model. Okay, 10 ISOs, intra-seasonal oscillations. That means 10 active phases, 10 break phages noticed, and then the details can be seen in one of the paper called the remote sensing letters. Okay, so and this was perturbed at different time scales, and then up to obtain the pool of ensembles. In our case, 40 ensembles of each phase can be determined, and then try to analyze it to know the predictability. So in our case, to examine the predictability, we have estimated a signal to noise ratio. Okay, where signal means it's a variance of intra-seasonal variability, where the noise means the mean square error difference between the perturbed and then control case, or maybe a similar case. Okay, so the predictability limit, what we have noticed, checked here, the predictability limit is the day where the noise is dominates the signal. So that means that is the day the model can give the better result, and up to that day, the model can give the better result. That is that's what we call limit of the predictability. Okay, So this is the active case in the control old model, active case in the assimilate model. So the predictability limit for this variable low level wind 850 hectopascal, you can see only 9 days. But in the case of assimilation of the new model, you can see up to 30 days. So there is an improvement, significant improvement in the predictability limit of the low level wind circulation. And compared to the break phase, compared to active, the predictability is always better in the break phase, as I just pointed out before, because the non-linear error growth is much slower in the break phase. So anyways, the 15 days in the control, but assimilation we have 18 days. Okay, this is the forecasted day. These are the 18 days, and this is the so assimilative model can give the better enhancement of the predictability limit of the active and break phases for the case of 850 hectopascal wind. And then coming to the rainfall case, this is the rainfall for the control. It is well expected. Dynamic fields can have the better predictability limit than the rainfall. Rainfall is always have limit is always lower due to various complexities. Anyway, so in the case of control, we have the only 3 days predictability limit because that is where the noise is dominating, right? The signal. But in the case of assimilation, we have 5 days. So that means there is 2 days better. Okay, in the case of break, we have the 5 days, the predictability limit. But in the case of assimilation, we have 9 days. So essentially, the predictability of active monsoon regime and break monsoon regime is also improved when we have the proper or realistic temperature and water vapor profiles in the model. So that then the monsoon system develops can be better, and also the forecasting also can be better. The predictability limit of for the different monsoon regimes also better. This is the key message of this work. So our results clearly indicates a considerable opportunity to improve the operational analysis and forecast with the hyperspectral data. That's what I have used in our experiments. So maybe this can be useful for further enhancement through the improved physical and modeling also, where you can put the accurate profiles in the convective parameterization schemes, and then in addition to that, such analysis, such things will be useful to understand the high impact weather events such as extreme weather events, floods, droughts, heat waves, cold waves, and many things. And also it can be used to know better understanding the subseasonal to seasonal time scale, especially with the special emphasis on high impact weather events. So this is the very important key message. These are other two problems that can be viewed in future directions. So with this, I would like to stop, and I'm really thankful to the Ocean Society of India organizers for giving this opportunity to talk. Literally, from my side, and probably viewers or the participants might.
Yeah.
But
so thank you.
Want to, yes, please always send me emails. But with this, I would like to take queries. Thank you very much, sir.
Thank you. So thank you, Professor Raju, for the wonderful presentation. So you have given a very good detailed outline covering the background of the Indian summer monsoon. Then you also dealt with aspects on the monsoon modeling and some of the key challenges and the ways to enhance the model fidelity. So this has been very clearly brought out in your presentation. You had actually covered on the classical criteria of the monsoon regime and covering especially the monsoon elements, several monsoon elements that you have highlighted in your presentation on the heat, low and monsoon trough, the low-level Somalia jet, on the Mascarene high, the Tibetan anticyclone, the tropical easterly jets, the monsoon clouds, and the monsoon rainfall. And thereafter, you have touched upon the theory, the monsoon theory, highlighting on the heat pump and the meridional gradient of the tropospheric heating. And it has got a very general outline of the monsoon circulation and the importance of this and how they affect the rainfall patterns. And thereafter, you had talked about the modeling aspect, specifically on the WRF model, which covers the different schemes like the PBL schemes, the microphysics, and the other fluxes which are being used for it. You also touched upon the moist and the thermodynamic structures, specifically on the lead and lag evolution of temperature profiles during different events. And some of the shortfalls in the model physics, where the moist and thermodynamic structures basically needs to be specifically highlighted. Then finally, you have also talked about the data assimilation, specifically on the 4D data assimilation, the advantages actually in assimilating the temperature and moisture structures for the better simulation of this ISM. And finally, you have also concluded by telling about the improvements in the quality of by improving the initial conditions through the data assimilation and the prediction of active and the break phases, specifically through the twin experiments. So it is a very wonderful presentation. Actually, you have touched upon a very complex topic and a very, very important topic actually, which is very important for it's basically the lifeline of India, actually, the monsoon. Now, let me see, there are some questions in the chat box. I have actually noted down some few questions which I would like to, of course, some of them are general in nature and based on your presentation. So the first question, actually, of course, I've noted it down in my paper. Yeah. Yeah. So the first question that I was a little bit curious to know about is there are some studies which says that there is a weakness that is happening in the strength of the Indian summer monsoon. There's a weakness that is noticed in the strength of the Indian summer monsoon. And of course, this study was actually reported from Pune, IIT in Pune, one of the research groups. Of course, they have actually related that to the sea level rise, which is on the western coast of India.
I see.
So how does it basically affect the variability of rainfall, this weakening of this monsoon?
Yeah, yes, sir, I agree. There are some studies saying that Indian subcontinent is drying because of the Indian Ocean warming, especially Roxy's group, and of course, Dr. Krishnan has also pointed out some time ago. That is true, but also there are some recent studies also showing that the monsoon is reviving, especially after 2002, and then giving the more rainfall. So now, but broadly, it's well established because of the Indian Ocean warming. There is a weak winds circulation from the Indian Ocean towards the Indian land region, and that actually, contributing downside of the rainfall trend of the Indian subcontinent. So, direct answer to your question is that if the monsoon is weakening, then the rainfall we are going to get less as a season. But within the season, other factors can contribute extremes, especially the rainfall more than 150 millimeter per day. So such events are, more frequent because of the global warming and of course the
That's
well-known
quite
gaseous cluster issues. Yeah.
so
So yeah,
that's quite interesting actually. So this global warming and the differential warming that is seen in the Bay of Bengal and the Arabian Sea basins, that definitely have an impact
yes,
on the Indian summer monsoon.
right, yeah, right, sir.
That's good. So now about the ERA products, you have actually highlighted about ERA products that is being used in the modeling. So how good are these ERA products for Indian summer monsoon modeling?
So this was actually done a few years ago. So at that point of time, ERA I is the one of the highest resolution data, where the resolution data. So we just used. But now ERA 5 came, and also the other regional reanalysis products also came. But it's broadly, especially coming to the circulation characteristics, still ERA I data is okay. Not that bad.
Okay. ERA I is, you mean to say ERA I is better actually?
Yeah, exactly.
And also in your presentation, you mentioned in one of your slides that the model simulated more rainfall. Like you have compared between model GPCP and TRMM.
Correct, sir.
What could be, why is it like that the model is predicting more rainfall actually? Like how can
this is the problem. Yeah, that is only the problem. Even the winds are, especially there is a lot of water vapor pumping, especially coming from the Pacific region and also from the Bay of Bengal region towards the Indian land region. So that excess moisture pumping into the land gives more and more rainfall.
Okay.
And then and then a lot of instable conditions, and then further is actually making it much more worse in the WF model, which we have actually resolved by using this assimilation of those two things, two ingredients.
That's very good actually. So have you looked into this effect of land use, land cover change, LULC changes in modeling this ISM actually?
So actually we have not checked this point, but few studies were already available. But this is land use, land cover things are mostly it's the regional thing. Probably I think this can be a good point to check. Actually, we have some experiments we have done with NIT Rourkela group. Let us see, like.
Okay. So my final question from my side, actually, this is the last question from my side. So recently, when we look into this rainfall patterns, we are finding erratic patterns of rainfall. Very erratic, actually, rainfall pattern.
Correct.
And very recently, I think yesterday, we are finding extreme flooding. For example, places like Cochin actually has been flooded now. Rainfall,
Yes.
heavy rain, yeah. So is it indicating that this monsoon is again reviving and gaining its strength, actually?
Yeah, especially in terms of extremes, I think this is true. It is always we are getting more intense and frequent extreme rainfall events across the Indian continent, and some, one side of, say, for example, West Coast. Even it is true for the foothills of Himachal. For example, Himachal Pradesh, we have in recent yesterday there was a lot of rainfall received and landslides, and these extremes is always actually.
Yeah, the Northeast is also receiving a lot of rain, actually. Northeast.
Lot of rainfall.
Yeah.
So within the system, in terms of extremes, actually, this is mostly connected to the climate change, global warming things. But broad scale, still the most total rainfall is still coming down, and let us see because that is mainly because of the Indian Ocean warming.
Yeah. Okay, fine. Thank you. So now let me look into the chat box. I think there are some few questions. Yeah, I can say actually that Dr. CVK Prasad Rao sir, actually, is from NPOL, Cochin. So he writes that it's a nice presentation, Dr. Raju. Must be very useful for the researchers and students on Indian monsoon. The question is, what is the accuracy of our monsoon prediction in terms of percentage?
Yeah, it's a very good question, and of course, it is the most complex to answer. I think now with the state of the art climate models that was being developed by the IITM CFS 2, we are able to achieve some extent, especially normal monsoon years. I think now we are better than the previous models. It's about 40-50% is, I mean, I'm not sure exact in terms of quantification, but we are much better than the previous. Hopefully, we can more extremes. I think this is still the problematic, but normal monsoons we are actually getting better accuracy.
Okay.
Yeah, but quantifying with respect to the percentage is difficult.
Yeah. It is a very complex process, actually, understanding this and modeling it. That's right.
Yes, sir.
So I think this is the only question that I see in the chat box. There are no other questions. Okay. So thank you very much, actually, Professor Raju. And on behalf of the Ocean Society of India, I sincerely thank you for this wonderful presentation. And thank you very much.
Thank you very much, sir. Really thankful, even though there are some technical glitches from my side. But hopefully we can resolve it, and then we can do better talks in the future. Thank you very much.
Thank you very much.
Thank you, sir. Bye, sir.
Bye.
Okay, bye. Yeah.
Bye, sir.